We have been discussing design of a processor where execution of each instruction is divided into multiple clock cycles. We have seen how the data path is designed, and today we will look at the controller aspects, how such a data path could be controlled. In the sequence of lectures on designing of the processor, we started with a very simple design where everything about an instruction was done in a single clock cycle. We noticed the problem with performance and there were other issues. So, we have moved to a different style where the instruction is divided into multiple clock cycles. So, we will look at how what are the actions which are done in different clock cycles for various instructions, and then by putting these sequences of actions together, we will try to build the flow of control for carrying out these instructions. We will then try to identify what control signals are required to control this data path in each of the control steps. For doing so, we will group the control signals into groups, and we will define some meaningful operations called micro operations. So, each instruction would be viewed as a set of micro operations which are done either together or in sequence, and that will somewhat simplify establishing a relationship between control states and the signal values. Finally, we will see how control states transit from one to other, and that will complete the design of control part. So, this is the starting point. We had arrived at this data path last time, where the key resources are memory, register file and ALU, and we have tried to use these as far as possible, so that there is a maximum utilization of all these resources. And you would also recall that all intermediate results we try to store in some registers. So, for example, that when instruction is brought out from memory, it is stored in instruction register. When data is read out from memory, it is stored in data register. Similarly, operands from register file are brought out into registers A and B, and the results of ALU operation are kept in a register called RES, short for result. So, now we need to control all these components. All the registers may not change their states in every cycle. So, each register will have a signal indicating when does we write something into those registers. We have controls for the multiplexers as usual, and similarly controls for ALU, register file and memory. But since we have new components like registers, multiplexer also have either changed in their size or in their organization, we will have to redefine some of these control signals. So, first of all, let us get back to the instruction and see how those instructions are divided into operations which are done in different cycles. Okay. So, what activity is done in which cycle, that needs to be clearly recorded before we can start working with the control signals. So, starting with R class instruction, in the first cycle we read one word from memory into instruction register, that forms the instruction. Address of memory comes from PC, and at the same time PC takes on the new value. So, both these operations are done concurrently within first cycle. In the next cycle, we read the operands from the register file and these two are brought into A and B. The addresses of register file are excuse me, are provided by the instruction and the relevant fields here are bit 21 to 25 and bit 16 to 20 for the second operand. So this corresponds to, the first one corresponds to RS, the second one corresponds to RT. Once again, what we meant by putting these two operations in a single box was that both of these are done simultaneously within clock cycle number 2. Okay, the next clock cycle for these instructions would see the actual operation being performed by the ALU. So, I have written in a generic sense A O P B, where O P is the operation as would be guided by the function field of the instruction IR 0 to 5, and the last cycle will involve transferring this result to the register file. The address comes from bits 11 to 15, which corresponds to RD or the destination register. So, this is how things have been divided, and we have made a careful choice of what gets done concurrently and what gets done in sequence. The second instruction we will take is store word, and the first cycle involves access to memory to fetch the instruction and updation of program counter. The second cycle involves bringing the registers out. Okay, we need again to access two registers, one which will participate in address calculation and second will carry the value to be written into the memory. So, with same fields of the register file, same fields of instruction, register file is accessed and registers are values are brought out in A and B. In the next cycle, we calculate the address, okay, by adding offset coming from bit 0 to 15 of instruction with sign extension to A, and this value is temporarily kept in this register called result. The last cycle will see an access to memory, where contents of RES will be used as an address and the data to be written into memory is B and memory write is performed. So, once again we require 4 cycles. The next is load word instruction. First cycle again is similar. The second cycle involves reading one register from register file. Here we need to access only A, because the second address corresponds to the destination here. What we read from memory will be stored in register RT. So, we need to read only one register, and in the third cycle we calculate address in the same manner. In the fourth cycle, memory access is performed, the data is read from memory, address is carried in RES and the data which is read is brought into DR. In the last cycle, we store the DR value into register file, the address comes from RT. Okay. So, this is a sequence of 5 cycles which complete load word instruction. Then we move on to BEQ. First cycle is same. In the next cycle we are doing lot of work. One is to access A and B, the two operands which need to be compared, and we also keep the result ready for the target address in case branch has to be carried out, because the ALU is free in this cycle. In the next cycle we are going to use ALU for comparison. So, in this cycle it is free, we calculate this address, but do not transfer it to PC immediately. We keep it in RES, the condition is yet to be checked. So, after checking the condition we will either transfer it or not transfer it. So, that is cycle 3, where the ALU will compare A and B, the two operands which were brought out from register file, and if the condition holds, then this new address is transferred to PC. So, this requires only 3 steps. Lastly, we look at the jump instruction. Again, the first cycle is same, and in the second cycle we compose this address of the next instruction by taking bits from PC and IR with okay, I missed out. Oh no, there is no sign extension here. This with 2 bit shift is concatenated with 4 bits of PC and then transferred to PC. So, this is done in 2 cycles. Now, you recall that the impression I might have given earlier was that this can be done in a single cycle, because only resource which is time consuming, which is required here, is accessing the instruction. After that, there is no memory access required, no ALU operation required. So, the total delay which we always used to think for this was max of T I and T plus, but why are we occupying 2 cycles here? The reason for that is we want to do these operations sequentially. The 4 bits we need to pick up from PC part is actually after PC has been incremented. So, after PC is incremented, one cycle is over. Okay. In the first cycle we are incrementing PC and the result is put back in PC. So, those 4 bits are picked up in the next cycle and put together with instruction. Also you would notice that it takes one cycle to fetch the instruction. So, although what is being done here is not a time consuming activity, but since it has to be sequenced after that, it is occupying additional cycle. So, in a single cycle approach, what was roughly taking equivalent of the memory access time or addition time, one of the two, now is taking more or less twice of that. So, this is just to recall that in the single cycle approach, the data path was like this, that we did instruction access and PC update, and directly we picked up the bits and formed the address, all right, and we said that the time required is max of T plus and T I, right. So, now if we have decided one clock cycle to be, let us say something which encompasses these, we are still requiring 2 cycles because of the need of sequencing things. These were the timings we had conceived earlier, and we were actually imagining the time for jump to be just this much. So, basically first clock period which will accommodate T plus or T I would be used, but we are doing something now, a very simple activity, but now since the time is quantized, discretized in terms of clock periods, we need to go beyond this and we can't use anything less than a cycle. So, we use 2 cycles for this instruction. Is that point clear? Why we have to go to 2 cycles? And actually, as we will proceed further, we will change things even for little worse, but that becomes essential. Okay, now we have seen the division of each instruction into cycles, the division of activity of each instruction into cycles separately, and once again we need to put things together to form overall flow of control. So, these are the 5 instructions or groups, and we will put their actions one after another in the same picture, so that we have a global view of the whole thing. Okay. Now, I have just to accommodate everything on a single screen, I have omitted some pieces of text which are more a matter of detail, but what I have tried to retain is all the destinations of the operation, wherever the results are going, and the main resources which are being used, right. So, for the first cycle, in all cases you would see that there is a access to memory. I have omitted some details here. There is the updation of PC, access of values in the register file, performing this arithmetic or logical operations, storing in register file, storing in memory, reading from memory, and so on. So, you can see that the essence of all these, the skeleton of all the operations has been captured here. And now, the task is to put these together. So, we have different instructions taking different cycles. You would notice some commonality, something is common, and that's where we can merge. But in the flow of control, at some point we would need to branch, because different instructions require different actions. So, the first part is first cycle is apparently common to all of them, right. So, we could start always with that action and a common state for all the instructions, and once things start differing, we branch to different states. So, each different boxes will correspond to different state in which the controller would be, and given a state of the controller, we would know clearly what actions are to be carried out in that particular state. So, what we are trying to arrive at is some sort of state transition diagram which would describe the control. So, at the moment we have 5 different chains or 5 different sequences, but we want to have a single graph which indicates how one moves from one state to other state and what action is required in each state. So, obviously, these can be merged. Okay. The first cycle seems to be carrying out same activity, and we can merge this. So, after merging, we have a single state and then a point where we are branching. Okay. Now, another important thing which needs to be noticed at this stage is we are contemplating a bifurcation here. We are splitting from this point onwards after first, but this requires us to look at the opcode. Okay. Before we can split, we need to see what the opcode is and which instruction or instruction group it is. But you can start looking at opcode only after you have fetched the instruction and brought into IR. Okay. So, now this is available, therefore, instruction is available to you second cycle onwards, and therefore, you can start looking at opcode second cycle onwards. Typically in a complex design, this decoding of opcode or understanding which instruction it is could also be a time consuming activity. The circuit which is going to identify a particular instruction would typically be allowed a full cycle to do it. Of course, we do not need that, but still the opcode decoding will have to take place in the second cycle, although we may not have second cycle fully occupied. So, therefore, practically this bifurcation or split must occur after second cycle, because if you have to go from this state to one of these states, we should know what the instruction is here, but instruction is known only after this first step is complete. So, it is only after second step we can branch off to different chains and do special action necessary for various instructions. So, therefore, second step will also have to be common. Now, let us see what is required to make it common. One thing is that not all instructions are trying to read 2 values from register file. Here you need 2 values, 1, here you are reading 2 values, here you are reading none. Is there any harm if all instructions read 2 values? They may use it or may not use it. The answer is there is no harm. Okay. It does not cause any problem in the functionality of the instruction. You might consume some energy in doing so, but let us keep that aside and agree to fetch both the values in all the instructions in an attempt to come up with a common action for the second cycle. The other thing you notice here are that address is being calculated here, which may be useful for branch instruction, and this value is kept in register called result. So, what what if we repeat this also in all the instructions? Once again ALU is free, we are not doing anything with it. So, if we occupy ALU in an activity which we may discard later on, still there is no harm apart from energy consumption. Also the result register is not holding any value which will get overwritten here. So, what we will do is let us try to make this as a common action for all the instruction. The only trouble comes with jump here, okay, because jump requires that we transfer a new value to PC, but that we cannot do for all the instruction. That would mean that the next instruction, after every instruction a jump will be carried out. Okay. So, therefore, we need to postpone this to the third cycle, right. We will do a common action in the second cycle, which is same as the BEQ action. All right. For all other instructions, there may be some superfluous or unnecessary activity which may get discarded, but there is no harm. The only harm which is occurring is that this action PC getting a new value is getting postponed. So, this is the picture with a common decoding cycle. So, this cycle actually is often referred to as decoding cycle or operand fetch cycle. Okay. So, now this is this jump instruction has taken another hit here, and we are eventually using 3 cycles for it. But please remember that this is an instruction whose frequency of occurrence is comparatively much lower than others, and therefore, the overall impact of this loss in the performance will be negligible. So, we do not really mind it, and now we have a very clean situation that there are 2 common cycles. By the end of first cycle, we know what instruction it is, and we are ready for the next value of PC. In the second cycle, after the end of second cycle, our operands, if we need, are ready in A and B, and a branch address is ready in RES if we need later on, and then we can move on to one of these separate branches. So, 2 further cycles are required for R class, 2 for store word, 3 for load word, 1 for BEQ and 1 for jump, and with that all the instructions will be over. So, now this is a cycle, this is a broader cycle which needs to be repeated over and over again. So, therefore, after these last states in the chain, we come back to this. So, now as far as controller is concerned, it is a small finite state machine with you can see these about 10 or so states, and it keeps on cycling through these. So, here you do the fetch, decode, you come to know what instruction is, follow one of these paths, and then you are ready for the next instruction. So, as long as power is on the processor, it will keep on going through this overall. So, this whole thing is called instruction cycle, and within this you have clock cycles. So, an instruction cycle would require 4 clock cycles or 5 clock cycles or 3 clock cycles as the case is, that is in this particular design. But there are of course machines where this range of number of clock cycles could be much varied. Okay, now we need to worry about what action we perform in each of the states. Okay, so these are the states, but before that there is another small improvement possibility here, which you will notice is that load word and store word have one more cycle common, where the address is being calculated, and we can actually merge that. And as far as load stores are concerned, we keep them together up to the third cycle, and then bifurcate into load and store. So, that reduces the number of control states by one more. So, total now I have how many states? 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Now, there are total of 10 states, and we will proceed further by looking at now the control signals. Okay, so this is back to the same data path, right. We have now roughly seen how we need to exercise these. Okay, what needs to be done for various instruction in different cycles. So, that picture has been made very clear now. We get back to each of the components which require a control and try to understand how we need to control it. So, for each of the register I have indicated a control signal. So, for PC write I am abbreviating as PW, this is IR write IW, DR write DW, then A and B have their AW and BW signals, and RES write is REW. So, they are signals, control signals, which will indicate whether a particular register changes its state in a cycle or not. Okay. And in which cycle the state is changed, we will know from this flow chart. So, we will always refer to now this flow chart or this state transition diagram and then decide the values. Now, we have also 1, 2, 3, 4, 5 and 6 multiplexers. Okay. Each one requires some control. So, control for this multiplexer decides whether we are accessing instruction or data, and accordingly the address comes from different sources. This multiplexer decides whether we are writing into RT or RD. This decides what gets written into register file. We are calling it M2R, memory to register, or it is ALU out to the register. Okay. The name of this signal is same RDEST we had earlier. This multiplexer is controlled by signal called A source 1, this is controlled by A source 2, and this we had earlier two registers which were two multiplexer which were handling the next PC value. Now, it is a single multiplexer with 3 inputs, and the control signal is labeled as P source or PC source. The memory, register file and ALU have their usual control signals, same as what we had in the single cycle data path. Okay. Now, you would notice that there are many more control signals as compared to the single cycle data path we had. So, I will not try to build the table exhaustively for all of these. What we will do is we will group the related control signals together and also identify the meaningful operations which we will call as micro operations. Okay. So, for example, PC plus 4 going to PC will be considered as a micro operation, right. It's a understandable action within itself, and it will affect some of the control signals in the data path. So, we will be grouping the signals according to our logical needs, and then try to look at things group wise. So, that will simplify the matter substantially. So, first we talk of a group of signals called PC group, which are related to PC, a program counter and its address. So, I will build a table where I list micro operations which are related to PC and the signals which are related to PC. So, the signals you can see right now, one is P source, the last multiplexer which is being controlled by this, and the write signal for PC I have split into, I have used two signals here, PWU and PWC, PC write unconditional and PC write conditional. You would notice that in some micro operations like PC gets PC plus 4, we are writing it unconditionally, okay. Whereas there was an operation like this where we are writing into PC with some condition, okay. So, this state will generate a signal which I am calling as PWC conditional, and a state like this or like this will generate a signal which I am going to call PWU unconditional. So, the signal PW which is going here would be derived out of these two. I will explain that in a moment. But let us see different micro operations and the signals which they imply. So, for doing PC gets PC plus 4, I make PWU as 1, this then I do not need to care, okay. And the source I am selecting is 1. Okay. So, three things going into this multiplexer, if you recall, is output of ALU directly, output of ALU through RES register, and then the address which is for jump instruction. So, let me just go back and check if I have indicated the correct source here. So, these are three inputs to this multiplexer: after the register, before the register, and this jump address. So, recall that we will write output of ALU directly into PC when we are doing PC plus 4. So, we do not bring register into picture, but the target address for a branch we are temporarily keeping into this, we are not directly transferring to PC, and therefore, when we transfer to PC we will take from output of the register. So, therefore, both paths have been provided. One more thing which you should see here is the way Z is going to be used. In the single cycle design, we used Z directly to control a multiplexer through AND gate. So, there was a signal coming from controller that was ANDed with Z, and then we controlled the multiplexer. Okay. So, basically we were making a choice between PC plus 4 and PC plus 4 plus offset, one of the two going to the PC. But now things are handled little differently, because PC plus 4 is sent to PC unconditionally in the first cycle. In the third cycle, the choice is either to transfer the new address or not to do anything. Okay. So, therefore, effect of Z will be brought into the way PW is being generated, right. So, in the first cycle we will have output of ALU directly through this multiplexer going into this. In the second cycle the address is calculated and kept in RES, and in the third cycle we will bring this out here without looking at Z, but we will look at Z and decide whether to transfer it or not. Okay. So, you will see that Z will come into picture when I define how PW is derived from PWU and PWC. Okay. So, this is next micro operation where we conditionally transfer an address to PC. Here I activate this signal and do not activate this signal. The source is 0, which means this value which is in RES is being taken. And the third case is that the jump address goes to PC. So, again this is unconditional. So, PWU is 1, PWC is X, and source is 2. So, in these tables I am going to write 0, 1, 2, 3 etcetera when the signal takes multiple values, more than 2 values. But actually you can think of the binary code of these going to the components and not this decimal value. So, apart from these activities, I would also like to define what is the default value of these signals. When I am not doing any of these, what should I feed to these particular points. So, the default value should keep everything inactive. Therefore, both write signals are 0, and then of course, once that is the case, the source does not matter. So, I put an X here, and here is how PW is derived from PWU and PWC. So, if PWU is 1, PW becomes 1 irrespective of what is it we have here. But when PWU is 0 and PWC is 1, then it is Z which dictates what we get here. If both are 0, then again Z gets ignored, right. So, basically I need one AND gate and one OR gate. So, the controller will produce these two signals, and with the 2 gates I will derive PW, which gets connected to the PC. All right, is that clear? Any question about that? Yeah, the third, this is the address which is being formed for jump instruction, okay. And it in one of the cycles, right now we are not worrying in which cycle what is happening, all we are worrying is that given an action like this to be performed, how do we control the data path. So, to make this happen, we need to make the unconditional write signal as 1, we do not care what PWC is, because you see when PWU is 1, okay, the values here do not matter, the result is going to be 1. It is a sort of overriding signal, right. But on the other hand, when PWC, when we want to activate PWC, we have to make sure that this is 0, because this will otherwise suppress that. So, PWCs do not care, and we need to select the correct value to go to PC. So, in all these operations, notice that PC is the destination, but the sources are different. So, there are 3 different sources. This is, and the multiplexer is selecting the sources. This is 0, sorry, this corresponds to 0 input of multiplexer, 1 input of multiplexer, and 2 input of multiplexer. This is how things have been connected in the data path. So, so that takes care of what the value is being transferred, and these 2 signals are taking care of whether this transfer is taking place conditionally or unconditionally. And the default, so there are many control states where we are not changing the value of PC, and there we need to keep both these as 0, and the value of P source does not matter. So, I would give some names to these, which will make things convenient in subsequent discussion. So, the first one I call as PC increment, this is branch, and this is jump, and this I call no op or no operation. Okay. So, just some names for convenience I have assigned to these. Now, let us look at operations which revolve around the memory. The relevant signals here are memory write and read control signals. This I or D, instruction or data, this signal decides what is the source of address for the memory, and these 2 signals decide where we keep the things which is coming out of the memory when we are reading from memory. So, this controls writing into IR register, this controls writing into DR register, and one operation is fetching the instruction. Okay. So, we are not writing here, we are reading, it is an instruction, and the multiplexer code for that is 0. The value which is being read is written in IR register. So, we keep this one, keep that 0. Next is getting data from memory. So, again we are reading, we are not writing, it is data. So, that makes it 1. We are not storing into IR, we are storing into DR. So, that is 1 and that is 0. Next is writing into memory. So, now we make write as 1, read as 0. Once again it is data. So, I or D is 1, and we are not storing anything into IW, IR or DR. So, both these are 0. You also might hear, it might occur to you that there is some kind of redundancy in these signals. It may appear that you may be able to derive one of these from others, or one of these from more than one of others. Okay. So, there are yes many possibilities. You might even notice that some signals can be totally omitted. For example, IW and MR seem to be identical. Okay. So, we can make such observation and simplify the controller design. So, it is indeed possible, but we will just limit at this and not get into those details. Finally, the default here is to keep write read both signals low, also the register load signals low 0, and then this does not really matter. Some convenient names for these: this is fetch, this is memory read, memory write, and no operation. Okay. So, now in later discussion, this once we say fetch, it would mean that this is the operation we are performing, and this is the set of values we are giving to control signals of this particular group. The third group is register file group, and here we are talking of writing signal RW, register file write, RDST. This decides where the address comes from when you are writing, whether it is RT or RD. This tells where the data to be written is coming from, whether it is coming from memory or from ALU, and whether we are writing into A and B register. So, reading RS into A, we make RW 0, RDST do not care, M2R do not care. These RDST and M2R will be relevant only when RW is 1. Okay. So, when you are reading, these do not matter. So, we give a write signal to A and B does not require. Similarly, reading into B, similar, except that we write into, we make BW as 1. Now, here it is writing into register file. So, we will make the write signal 1. We need to define our DST. So, it will be 1 in this case, M2R is 0, and we are not modifying A and B. This is writing DR into register file. So, again RW is 1, but this has a different value, RDST is different because the address is coming from different points, and also the values being written are different. AW, BW both are 0, and default is to keep RW 0 and to keep. So, we do not make any change in the state here. So, all write signals are kept 0. So, once again you would notice that these two signals RDST and M2R are complementary of each other. Okay. So, one could reduce the signals. Names for these: RS to A, RT to B, RES to RD, MEM to RT, and no operation. Okay. So, these 5 names I am going to use later on. Finally, the ALU group, the signals are OPC. It is a 3-bit signal, sorry, this is a 2-bit value which we derived from the opcode. Okay. What goes to ALU finally is a 3-bit signal which will look at OPC and the function bits, and that part of the circuitry will be totally unchanged. Then we have these multiplexer control signals A source 1 and A source 2, and signal which controls writing into result register. So, a micro operation which we saw earlier is appearing here also, because doing PC gets PC plus 4 influences the PC group of signals as well as ALU group of signal, because we need to ensure that addition is done here. So, OPC, we will look at OPC later, but look at the source and get back to this diagram. Yeah, A source 1 has a choice of PC and A, and A source 2 has a choice of B, 4, this offset for load store and offset for branch. So, these are the 4 possibilities here and 2 possibilities there. So, let me put all these together actually. Yeah. So, A source 1 has value 0 or 1, it 0 for PC here and 1 for A. Okay. A source 2 has 4 possibilities, 0 for B, that is here, 1 for 4, 2 for load store offset and 3 for branch offset. Okay. For this operation again we are comparing A and B. So, it is like this as far as source are concerned, 1 and 0, this and this. Okay. This is indicating whether we are writing into RES or not. So, in these 3 steps we are writing, here we are not writing into RES, here we are not writing into RES, and this OPC encoding is same as what we had done earlier. For those instructions where we have to simply perform addition without looking at anything else, we make it 0. So, we had done this for load store instruction. Okay. And now even for these address calculations we will use 0, because our logic would be that whenever there is a 0 here, that ALU controller will ensure that ALU performs addition, and 1 would mean that it performs subtraction unconditionally, and 2 it would mean that we look at the function bits. Okay. So, same encoding is used and accordingly we filled this up. The last case is the default case where these are do not care, does not matter what ALU does as long as the result is not written anywhere. So, we ensure that REW is 0 and ALU may do something which is do not care. Okay. So, now with this done, we have seen the relationship between micro operations which we picked out of that flow chart, and how they assert various control signals, what values they imply for various control signals. The names of these are PC increment, arithmetic, memory address, PC address, branch and no operation. So, now I can tabulate these, but before that let me redraw that diagram with these new symbols put in the boxes. Okay. So, instead of those assignment statements, I have replaced those with the new micro operation symbol which I have described in previous few slides, right. So, for example, in the first cycle I am doing fetch and PC increment, in the second cycle I am doing RS2A and RT2B and PADDR, all these 3 are done concurrently within the second cycle and so on. So, all these signals have been all these micro operations have been put into appropriate state. Also these states could be numbered CS0 to CS9, right. Now I need basically 2 tables. One table will define for a given control state what micro operations I perform, which will also directly imply what are the signal values for various control signals. Okay. So, that is one table. Next table would define that given a control state, what is the next control state, and this transition may be conditional. It will depend upon the way I am bifurcating. So, it will depend upon the opcode. So, let us see both these tables one by one. So, first relationship between control state and signal values. So, I will not list the signal values here, I am only listing the micro operation in the particular group. So, these are the 4 groups I identified: PC group, memory group, RF group and ALU group. And in CS0 the operation I need to perform is PC increment. This actually shows up here also, as I mentioned that it requires to control signals at both the ends, and in memory group the operation is fetch. In CS1, I am fetching these operands and calculating branch address. In CS2, this is the first distinct state for R class instruction. So, I perform the arithmetic operation here, and so the R class instructions go through CS0, CS1, CS2 and CS3. In CS3 the value gets written, and all those which I want to keep inactive, you will find there is a no offsetting there. So, here the result is being written into register file. Then C4 is the common state for load store. Here memory address gets calculated. Then C5 completes the store operation. We have a memory right here. C6 performs memory read operation, and C7 performs transfer of data from memory to register file. Okay. C8 completes the branch instruction. So, again branch operation, branch micro operation shows up in PC group as well as in ALU group, because it requires a comparison here and it needs to change the state of PC. So, both these get influenced, and C9 completes the jump instruction. So, it is influencing this PC group. What I can do, but I will not do that here, is that each of these micro operation symbol replace it by a bit vector. Okay. That bit vector defines the relevant control signals. Once I have that, I also encode these 9 states in binary. So, you can use 4 bits to encode the state. I form a truth table where this is the input, the code of the state is the input, and the bit vector which I write here are the outputs. So, these are the control signals which go from controller to the data path. The second part of the control design is how control state transitions take place. So, again for each of the states, let me just fill it up. For each of the state, I am defining the next state, but the next state could be different depending upon what is the opcode value. So, from CS0, I am unconditionally going to CS1 in all cases. From CS1, one goes to CS2 or CS4. For load store, it is common again. For branch, it is CS8. For jump, it is CS9. From CS2, which is for R class instruction, go to CS3, and these conditions will not occur. Once you have gone to CS2, you know that it is R class instruction and others are not relevant. So, you can see that R class instruction go through CS0, 1, 2 and 3 and back to CS0. For store instruction, you will start with CS0, go through CS1, CS4, CS5 and then CS0. For load, it is CS0, CS1, CS4, then CS6, CS7 and then CS0. For branch, it is 0, 1 and 8 and then 0. For jump, it is 0, 1, 9 and then 0. So, now what kind of truth table I have here? Here the opcode and 4 bit of the control state, these form input of one combinational block, and the next state value or the 4 bits which encode the next state are the output. So, with if you implement these two tables, okay, the table shown here and the table shown in the previous slide, namely this one, you can use 2 PLAs to implement this. So, these 2 PLAs plus one register holding the control state, 4 bit register holding the control state will form the controller. Okay. So, I will draw that picture next time and look at some alternatives. So, today we will stop at this. Let me just summarize that we saw how instructions get divided into sequences of micro operations, how we group the control operations, control signals and then defined relationship between micro operation and control signals. Then we associated control states with the micro operations, and we also identified control state transitions. Thank you.